Here are some practice synthesis problems that we can work on. They involve any and all reactions that we've learned about this semester up to the end of the alkyne chapter. So anything we've learned could be fair game here, and this would be something that you might see on perhaps exam 3, but most likely on the final exam or perhaps quiz number 4. Here are some practice synthetic problems that could use any or all reactions that we've learned about this semester up to and including the end of the alkyne chapter. And they would be most appropriate to practice for probably the final exam or maybe a final quiz in our class. Exam 3 may not have as much alkyne information as certainly as the final exam will have. So here we have some practice in using basically any reaction that we could have used and learned this semester. So when working synthesis problems, it's best to work backwards. If you try to work forwards, sometimes maybe if it's only 2 steps, you can easily work, like this, find something here, and take it to the product. But most likely, you're going to need to work backwards. And so working backwards, we look at the product, and we decide how we can make probably whatever functional group is present in the product. And we also understand that the carbon skeleton that we started with most likely will appear somewhere in the product. And if we observe, in this case, that there's 5 carbons, and now if we count 7 carbons, so we have to add 2 carbons. That's a good point to understand. We need to add 2 carbons here. We need to make a ketone. This is a methyl ketone, so that's a special kind of ketone that we learned how to make from alkynes. So if I take that alkyne and I react it with H2SO4, water, and HgSO4, mercury sulfate, we can essentially hydrolyze the alkyne and install a group at the interior carbon where it's a little more stable for cation formation, and eventually we end up with a methyl ketone as we see in the product. Alright, so that gives us a new target. We have our 5 carbon alkene, we have a 7 carbon. Let me just make sure I still have 7 carbons here. We don't want to lose carbons inadvertently. We still have a 7 carbon alkyne here. And so it looks to me like we have an alkyne, and probably we want to be able to form that bond, because we know how to form the bonds next to alkynes. That's simply deprotonating the alkyne and adding the appropriate alkyl halide, right? So we could do this. The appropriate alkyl halide in this case is a 5 carbon chlorine or bromine or whatever you want to use. And the alkyne is that. Right? So we've taken acetylene, we've removed one of its hydrogens via the NaNH2 reagent, and now we can do an SN2 type mechanism here. That's not it. We can do an SN2 mechanism and produce our last intermediate. So now, how can we take this molecule? Some of you may be thinking, how do I turn it into this alkyne? But really, I think this is a 5 carbon piece. This is also a 5 carbon piece. How do I turn it into that bromine? And I think we can turn it into that bromine in one step. We use HBr and peroxides. We can put a bromine in an anti-Markovnikov fashion on the end of the alkene. So don't get caught up in the fact that we have to follow a certain order. Here we're actually bringing in the nucleophile as a reagent that we just get off the shelf, and we're creating the electrophile from our starting material, and that's perfectly reasonable to go around. But I think a lot of us get caught up in the fact that, well, this needs to be converted somehow into a nucleophile, then we can bring in an alkyl halide to react with it. Well, that's not necessarily always the case, as you see here. All right, the second one on this page involves a 6-carbon chain. Let's change colors here. And it looks like we have a 6-carbon chain to end with. We've created a stereocenter, and we've indicated that we form both enantiomers here. So there's no stereo control. It's just good to note that we've created that stereocenter, but we also create both the R and the S versions of that. And so how do we create this functional group? Well, remember from chapter 9, that is simply water plus Br2. Hydrohalogenation, I believe is what it's called, but more importantly is that we can remember the reagents. So remember that creates the bromonium ion intermediate, which is then opened with water as the nucleophile on the more substituted carbon of the bromonium ion. And this carbon will be the more substituted carbon when we make our bromonium ion. So that's a fine way to do that. That will give us Br on the less substituted, OH on the more substituted, and of course it will form both enantiomers. So now how do we create this 1-hexene? And this again has 6 carbons, and we start with 6 carbons, so that's not really a problem. What we need to do then is somehow form an alkene at that position, and that's actually reasonably easy to do. We just need a large bulky base to form the Hofmann product. So a large bulky base will remove one of these methyl hydrogens on the outside, giving us 1-hexene. We can react that with Br2 and water, and we have our desired product. All right, third one, we have, looks like a 5-carbon alkyne, and in this case, we have a 7-carbon product. And if we look more carefully at it, we have functional groups on carbons 4 and 5. And if I number our starting material sort of in the same way, we observe that there's a functional group on carbons 4 and 5 in the starting material. So that gives us a clue as to how things might proceed. And we need to add 2 carbons to our starting material. And we need to, of course, produce the anti-bromines. And it's important that we recognize that we need the E version here, because that will give us the anti-stereochemistry that we want. If I were to turn, let's say I turn this into a wedge, that would be syn, but if I rotated my molecule like this, now it looks like it's anti. And so this would imply I need some sort of Z alkene to start with in order to put these bromines in that position. So be aware how the stereochemistry requirements are. Let's see if I can delete these quick. There we go. Okay, so I need an E alkene in this case. At other times we might need Z. And we know how to make an E alkene. But I think at this point it would be useful to think about how to add the 2 carbons. And we know that we can take the starting material, NaNH2 as the first step. That deprotonates right here. And then we can add, in the second step, the 2 carbons, and then we end up with this 7-carbon alkyne. And that can be turned into the alkene via our sodium in ammonia reduction. That gives us the trans-alkene. So that's why it was important to recognize that we needed trans, because we could also produce cis if we used different reagents. So here's the 3-step process. We had to add 2 carbons at the beginning, then we needed to change our alkyne functional group into something that would react with Br2 to give us the anti-dibromide that we saw in the product. Okay, the fourth one, we have a 2-carbon acetylene, of course, and then we have 6 carbons over here. So somehow we need to add 4 carbons. And if we look at the 2 sort of areas on our product, we have 4-carbon chain that has nothing of interest on it, Then we have the 2-carbon chain that has the functional group. So that most likely came from this 2-carbon chain. So we know that we can add 4 carbons, same way we did it on the previous problem on this page. NaNH2, 4-carbon chain, and there's our 6-carbon alkyne. And so that leaves us with a handle, some way that we can manipulate to get the secondary alcohol. In order to get to the secondary alcohol, we've learned that alkenes can be hydrated. That's probably the easiest way for us to get to that secondary alcohol. There are other ways that we'll learn about in the second half of the textbook. So if we do this, we can, let's just use HgOAC, water, follow that up with NaBH4. That will give us water addition across this alkene. The OH will add to the more substituted carbon. How do I get to this alkene from my alkyne? Well, I could just use H2 and Lindlar's if I wanted to. That will give me the E version, but there's no stereochemistry or stereoisomerism here with this alkene, so that doesn't matter. Or I could use the Na in ammonia, NH3, that I used to make the Z version, whichever one you want, whichever is easier, essentially, if you're in the laboratory. Probably choose H2 and Lindlar's catalyst, to be honest with you. But again, here we have a nice 3-step sequence. We observed that we needed to add 4 carbons, and that there was a functional group sort of on the 2-carbon, which could have come from one of these alkyne carbons. So the alkyne is used to add extra carbons, and then we retain the use of that functional group to manipulate it to get to our alcohol.